So, good morning everyone. This is Nandeep from MIDAS. Today we will be modeling the substructure part of the model created using the FCM wizard. Now, since this is a mass webinar, the attendee mic have been muted to avoid any disturbances. If you can hear my voice, please raise your hand by clicking the button shown by number 2. Everyone, can you hear my voice? Okay, so I have enough raised hands, so I'll start giving the webinar now. If you have any questions during the webinar, please type those in the box shown by number 3. And these questions should be answered based on the time available at the end of the session. Anyway, a document with all the questions answered would also be sent to you at the end of the webinar series, that is, after tomorrow. Okay, so now moving on with the content. So in previous session, Mr. Shubham covered how the material property and section property could be defined. Also, the superstructure of the bridge and the integral piers were made using the FCM wizard. It was shown how to provide the tendons in the structure as well as how to give the pre-stressing force to them. Show the image shown over here. That was the part that was covered in yesterday's session. So as shown in the image here, this is what we'll be aiming to do today. We'll be doing the substructure modeling manually for the end supports. We'll be defining structure boundary and load groups and why these are needed. We'll be defining the links. I'll let you know what links are. We'll be modeling the bearing. We'll define the boundary conditions. The loads that would be applied to the structure, like SIDL and temperature loads. The time-dependent material property, that is, the effect of creep shrinkage and change in compressive strength with time. And we'll try to cover the construction stages as well. Now moving on to the substructure dimensions. So these are the pier dimensions that we'll be constructing today. The girder center top position is as shown 1.975 meter at an offset in the lateral direction, and the bearing top is 2.7 meters below the girder center top position. The height of the bearing with the pedestal is 300 mm, and the pier cap is 6.3 meters wide and 6.3 meters long and 3.4 meter wide. The height is 1.5 meter near the pier and 0.8 meter at the edge. And the height of the pier is taken as 20 meters. So first of all, let us start by modeling this. Okay, so this much was done yesterday. So now to make the, first of all, let us make the bearing positions at the girder bottom. So to do that, we'll select this node, and as shown in that figure, it's at an offset of 1.975 meter in the lateral direction and 2.7 meters vertically. So we are using the translate node option. So translation in X. This bridge has even another simply supported part after the, this FCM location. So that's why the bearing are at an offset as compared to the pier cap. I'll show the slide again. Here, the bearing are at an offset of 1 meter from the center line of the pier cap. So we'll be moving the pier cap center line back as well. I'll show everything. So first all, So this is the first bearing point. This is the second bearing point. Now we'll be making the bearing bottom points. Those are 300 mm below. So now first of all we'll make the pier center point, pier cap center point. So as shown in that figure, it is at an offset by 1 meter. So in x direction -1, in y direction 0, and in z direction -3. Okay. The bearing bottom has to be connected to the pier cap. So we'll also moving back these points by 1 meter. You have to make points to mark the total width of the pier, because the pier cap would be tapering. As well as the edge of the pier cap. So now we'll define the section properties for the pier cap and pier. So to define this, we'll go to properties, section properties. And these are the section properties that were defined yesterday. So we'll be adding to them. First of all, the mid part of the pier cap, PC mid, user defined section. The height is 1.5 meter. The width is 3.4. Offset is center top. And we'll add the tapered part of the pier cap. So we go to tapered sections, we select solid rectangle. We give it name as PC tap. Okay. So I section is 1.5 by 3.4 and the J section is 0.8 by 3.4. This tapering is linear. The offset is center top. Okay. And we'll also define pier while we are at it. Okay. So now we'll be making those elements. So we go to node element tab and we get create elements. The material is substructure material. The section is pier cap mid first of all. So we make it here and we make it here. Now we'll select the pier cap taper. This node to this node and this node to this node. Now as you can notice, the tapering is happening over the length of single element only. However, this is not what we want. We want this tapering to be smooth from the edge of the pier to the edge of the pier cap. So for that we have to create a taper group. Yesterday for the superstructure, this taper group was handled by the wizard itself. But since we are manually doing the pier cap, we'll have to create the taper group manually. So for that, we again go to properties. We go to taper group. Give a name, say PC tap again. And elements we have to select. These elements and these. It's linear tapering. We just go and click add. So now you notice that the pier cap is tapering smoothly from edge of the pier to the edge of the pier cap. Okay. Now we'll be modeling the pier. So for pier again I have to translate the nodes. So you go to node element, translate. This time we'll use the unequal distance option. So pier cap is obviously, so we'll have to translate the nodes in Z direction. So select the center node. We have to first translate at the bottom of the pile cap and then the overall length of pier, that is 20 meter. Sorry, I mean bottom of pier cap and overall length of pier. So minus 1.5 and minus 20. So the bottom node and this node is created. So now we'll again create the pier element. So go to create, select sub, the pier element. Okay, so this is done. I'll again be moving to presentation. I'll show you the pile layout. Okay, so this is the layout of the pile. So at the end support, that is the pier we just created, the piles are 1.2 meter in diameter. The pile cap is 2 meter thick and its dimensions are as shown here, 8.9 meter by 5.3 meter. Okay. So first of all, we'll have to give the pile cap. So that will be defining by means of a plate element. So going back to the model, we can go to properties, thickness. I'll be defining the plate thickness for both the pile cap at the end support and the pile cap at the integral piers. The pile cap at integral piers are 4 meter in depth. So add thickness ID 1 to plate offset. Now we are giving plate offset because when you are creating element center and how you have to give an offset of center top to model the element. Similarly over here for plate also we have to give an offset. So since this is a 2 meter plate, I'll give an offset of 1 meter. So this is like the center bottom option. And then the 4 meter. Again I'll give value as 2 meter. Again this will be center bottom kind of. Now to avoid confusion, I am clearing the hidden view. Now to create the pile cap, as shown in the slide, the dimensions were 8.9 meter by 5.3 meter. So first of all, I'll be creating the right bottom node of the pile cap. To create that, I'll have to translate the pier bottom node by 4.45 and 2.65 meter in the x and y directions respectively. Again, to translate the nodes in x direction by 4.45 in y direction by minus 2.65 and in z direction by minus 2. Now I'll have to create, I'll be creating a line element and that will be later extruding it into a plate element. Okay, so line elements will have nodes where at the pile location, at the center of the pile cap and at the edge of the pile cap. So this is the bottom right node. Using the unequal distance, we will create rest of the nodes. So piles are 850 mm inside from the pile cap. So first would be it has to be in y direction, minus 0.85. Then the center to center distance between piles is 3.6. So I'll be making two nodes at minus 1.8 meter and then again one node at minus 0.85. Got the plan. Oh, it seems like I made an issue in taking the node for the first time. So we'll just verify that. Yeah. So these have to be translated in the positive y direction. Sorry for my mistake. Yeah, so this is proper. So now we'll be creating a line element. Okay. Now this line has to be extruded in minus x direction for 8.9 meters. There are 6 piles in all, right? With pile offset as 0.85 with the pile cap edge, and the distance between piles is 3.6 meter. So we go to extrude from line element to planar element. We'll remove the source since this line won't be needed. Now for pile cap we have to select the substructure material, and this pile cap is 2 meters thick. So this is okay. We'll go for the unequal distance option. In x direction, we'll move it by minus 0.85, then 2 at minus 3.6, and then again minus 0.85. Okay. So now I'll show you the 3D view. So this is the pile cap. As we had given the offset value of 1, now you can see that though I had created the pile cap 2 meters below the pier location, but the bottom of pier and the top of pile cap are at the same location now. And now we'll be creating the piles. There were 6 piles in all, right? So we'll be selecting the pile nodes and we'll be extruding again. Now at the end supports, the piles that are used are 1.2 meter in diameter and the length is 28.5 meter. So first 0.5 meter is extruded and then the remaining 28 1 meter elements are made. So first of all we'll be defining the pile section properties. Say 1.2 meter pile. Okay. User defined, the diameter is 1.2. Apply, and we'll make now the 1.5 meter pile. Okay, right. So the two 1.2 and 1.5 meter piles are made. Okay, so for these nodes we'll translate them by first we'll select node to line. We'll select the material sub. We'll select the section as 1.2 meter pile, unequal distance in z direction. We have already selected the pile nodes. Okay, one node is missed, so we'll select that. And we'll enter the distances as minus 0.5, 28, minus 1. So now the entire end support at the first location is created. Okay. Similarly, we'll create the substructure for the integral pier at the integral pier obviously. So its layout is as shown over here. The pile cap is 29 meters long and 6.5 meters wide. So again, we'll be creating the bottom right node, which is at 14.5 meter in the x direction, minus 3.25 in the y direction, and minus 4 in the z direction. So we'll translate this. Translate 14.5 minus 3.25 and minus 4. Again, we'll translate these in the y direction. Unequal distance. These piles have an center to edge of the pile cap distance of 1 meter, and center to center distance of piles is 4.5 meter. So first of all, we will be making as before a line element. So I'll be translating the nodes first. The distances are 1, 2 at 2.25 and 1 in y direction. Now we'll be creating a line element joining these. Yeah, while you are creating the line element like this, you have to select this intersect node option. So that way what will happen, though you are connecting the first node and the last node, automatically the elements would be found for the intermediate nodes as well. It won't be one single element, but it will be 3 or 4 elements as depending on the number of nodes. Okay. So now we'll be extruding this again to create a similar pile cap. We'll select the line to plane option. We'll select the substructure material. The plate thickness is 4 meter. Unequal distance in x direction. And we'll be moving it by 1 meter, then 6 at 4.5, and then again 1. Yeah, in x these have to be minus. And we'll say apply. Okay, so this is the pile cap is created for the integral pier. Now integral pier has 26.5 meter long piles. So we'll just activate the integral pier pile cap to avoid confusion. So to activate certain elements, you have to select those elements, and then you have to click this button. This is the activate button. So it will activate the selected elements. So now this is selected. We'll go to the plan view. We'll select the pile nodes. We'll select node to line option, substructure, pile 1.5 meter dia option in z direction, minus 0.5, 26 at minus 1, and we'll say apply. See, piles and pile caps have been created. To activate the entire structure, you have to click this button, or you have to press Ctrl A. Everything would be activated. So a similar structure and elements are there at the second integral pier. So we'll just move these structure, copy this pile cap and piles to the second integral pier. To do that, first of all, we need to know the distance between the piers. So we'll go to query nodes. We'll select node number 1 and then node number 2. Now here this dx, dy and dz are shown, right? So that is the place where we want to copy the new elements. So we'll select the elements. We'll go to node element, translate, Now select copy over here by equal distance. Over here you will have to enter these coordinates. So what you have to do is we'll be taking this distance. Paste it over here. Okay, wait a second. And here we'll copy the node attributes, element attributes, and we'll say apply. Okay. The other way would be it's actually dynamic as well. So you just undo it, select the elements, click at this location, and you click. First of all, you click here. From here, you take it to here and apply. Okay. So this way, similarly, you can do for the end Pier as well. But before I do that, I'll be talking to you about the links. Okay. So in this, we can see that, it's a line element. These are the, top of the box, the bottom of the box, but in reality, there is no connection between them. And it has been stated in codes that plain element remains plain. So these, it is basically a rigid body. So these have to be connected by a rigid link. Now, for a rigid link, it is assumed that a rigid link has very high stiffness and the distance between the connecting nodes remains constant if the rigid body option is used. So for that, we'll be creating the rigid link from the center girder top position to the bearing top position. So for do that, let's go to boundary. We go to rigid link, the master node. Yeah, rigid link has one master node and one slave node. So whatever forces or displacements happen for the master node, same values would be applied to the slave node as well. So one rigid node can have several master nodes. So in this case, the master node would be the box girder top, and the slave nodes would be, so first of all, let us say rigid body option. The slave nodes would be this and this. Apply. Okay. So now if you will view in 3D, it is shown that the top of the box is connected to the bottom of the box. That is the bearing top. Okay. So now we'll model the bearings. So to model the bearings, we have to use the elastic link option. Okay. In elastic link, you can enter the displacement stiffness as well as the rotational stiffness. So if your bearing is say simply supported neoprene kind of bearing, then it will have stiffness only in vertical directions, and laterally and longitudinally it won't have any resistance. But say if it's a guided bearing, then obviously it will have stiffness in vertical direction, and its lateral stiffness will also be very high, while longitudinally it won't have any stiffness. So those values you have to enter over here. If any value is kept as 0, that means it is free, it has no resistance. And in case of links, the x direction is always along the link. So to show that, I'll just create a link. First of all, I'll give the x stiffness as 10 raised to 8, very high. And say I'm creating a bearing with lateral restraint. So this I'm keeping as 10,000. Okay. And yeah, I can even copy the elastic link. So say I'm copying the link by 3.95 meter in y direction. Okay. Sorry. 3.95, and the two nodes are this and this. So if you'll notice, the X is along the bearing and Y and Z are in the lateral and longitudinal directions respectively. So I have created bearings with high lateral resistance and no longitudinal resistance. The vertical stiffness is obviously very high. So that's why this is how bearings could be modeled. And after the post-processing, we'll see that we can check the force in the links, so which could directly be used to design the bearings. Again, going for the overall view and the view at the pile cap. Here also it feels like the bearing is connected to the pier cap, but in reality, again, that is not the case. So we'll have to use rigid link to connect this node with this node. So we go to rigid link option again. Select this as the master node, rigid body option, and this as the slave node. Similarly for the other location, this as the master node, and this as the slave node. Similarly, we will connect the pier cap to the pier. This is the master node, and this is the slave node. Okay. Now, again here also the pier is connected to the pile cap. So this will be the master node, and this will be the slave node. Okay, now here the pile cap, it is modeled as a plate. However, practically, no matter how thick a plate is, it will obviously undergo some deformation. But when we are designing the piles or the pile cap for that matter, what we assume is the pile cap is acting as a totally rigid body. To simulate that action in model, what we'll have to do is we'll have to connect this pile cap center node to each and every pile node via a rigid link. So each and every pile will act uniformly together. Otherwise, what will happen is the central piles will have more reaction and more load as compared to the edge piles. So to avoid that, we'll again be making rigid links over here. This is the master node, and rigid body action is selected. So now the slave nodes are okay. Oh, sorry. Master node is this, and slave nodes are this. Okay. This, and slave nodes are okay. So this is how it can be done. Similar could be used at the integral pier, but we won't be taking time in doing that as we have limited time. Now to translate this for the integral piers, it was simple. We just had to translate it and it was done. But if you'll see in plan, all of it is straight. But if it has some angle, then what you have to do is you have to translate and then you have to rotate the structure as well. So I'll be showing that for the pile cap and the pile. Okay, so say we have to the actual distance going by the drawing, the translation that needs to be done is around 149 meter in X direction and 77 meters in the Y direction. Okay, so we'll go to nodes element, translate element, then equal distance of okay. We have already selected the elements. Copy node attribute, element attributes. One, we'll be copying this and we say apply. So the pile cap has moved to the end pier location if you in plan. Okay. Now here it is showing that it is in alignment with parallel to the x-axis, but in fact it has a beta angle rotation of 54.8 degrees. So we'll have to rotate the entire thing. So we go to, we'll select the relevant elements and we'll use the rotate node options. Okay. So one time the angle of rotation is minus 54.8 degrees. Okay. About axis defined by 2 points. So I have to select this option. Okay. So the first point is this, and the second point, obviously, since it is going to rotate about a vertical axis, we can simply select this itself and we'll just give it some z coordinate. So we are giving it z coordinate as 4. Okay, we have to move it and apply. Okay. So now if you view in plan, see the pile cap is rotated. Okay. So once this is done, now let us talk about groups a bit. So I'll be moving to the presentation again. So these groups are needed to be defined if you want to activate or deactivate some element, some load, or some boundary during the construction stage. Only structure, load, and boundary groups can be activated or deactivated. Tendon groups are created just to view the results of a certain number of tendons together. I will be covering more on the construction stage at a later part, but why I am showing this? Because now I'll be giving the boundaries, and while giving the boundary, I'll have to define the boundary group. I'll be giving the boundary condition for the piles that we have made. Okay. So if I want to select all the piles with 1.2 meter diameter, then I just double click on the section properties over here. All the piles are selected. I'll go to the boundary, and MIDAS Civil we have an option for integral bridge. So what here we can do is we can give the abutment spring or the pile spring constants. Okay. So first of all, I'll be creating the boundary for that. Say the boundary name is end pier piles. Okay, and we are adding it. So we have selected that group. I've selected the pile spring option. Say the soil type over here is sand. Okay, I'm taking ground at 2 meter elevation. That 2 meter, that means the Z value is 2 in the MIDAS model where practically the ground is. Say the pile diameter is 1.2 meter. These values we are keeping as it is, and the modulus of substrate reaction, say it is 80,000 kilonewton. Okay, and we say apply. So the pile springs, that is what will be the reaction of the pile in X, Y, and Z direction, that would be automatically calculated, and those would be applied to the piles. So you don't need to calculate the stiffness at each and every point. If now the soil type is different from obviously the soil layers would be changing. So accordingly, you may select relevant number of nodes. You can give springs like this. Then you will select the other layer of nodes where the soil properties are changing. You can enter those values. So the spring constants for those would be made available over here. So this eases a lot of work. Okay. Now I talk about the loads that we would be covering today. So MIDAS civil, you can specify a lot many types of loads, nodal loads, element loads, pre-stressing, thermal loads, right? And the various types and cases are given at the right side. In this webinar series, we'll be covering the self-weight, the pre-stressing loads, the SIDL for the wearing course, the temperature, that is element temperature, temperature gradient, as well as the moving load. However, the moving load would be covered in tomorrow's session. Today we'll be dealing with the temperature loads, as the pre-stressing load, self-weight, and other loads are already defined in the previous session. Achha, temperature load and SIDL loads. Okay, so I'll be moving back to the model. Now this is an unfinished model, so I have already created a finished model to work on for today. Okay, so this is how the finished model would look with pier caps, pier at all the locations, and the angle of rotation being properly provided and everything done. Okay, so now we'll define the different loads that have to be given. So we'll go to, first of all, we'll have to create those load cases. So in static load, we'll create static load cases. First one would be for, say, SIDL. Okay. Type is dead load for wearing surfaces and utilities. Okay. Wearing. We don't need to give the description, but it is a good practice to avoid confusion as to what load was considered in this particular load case. So we'll add that. Let us create temperature load cases as well while we are at it. So say temp rise. We'll go to temperature load case. Add temp fall. Add then plus temp grade. This is the temperature gradient load case that we are defining. Okay. We'll select the temperature gradient, add, and the negative temperature gradient. Okay, so these are the loads we'll be dealing with today. Okay, so yesterday it was discussed that the width of the structure, it is the deck, that is 10.13 meter, out of which 1 meter on each side is for footpath. So here I will show you how to apply the wearing course load. So the width for wearing course is 8.13 meter. Assuming a thickness of 100 mm and density of wearing course material as 20 kilonewton per cubic meter, the UDL for wearing course works out to be around 16.26 kilonewton per meter. So what we'll do is, we'll go to the hidden view. We'll select the top elements. Okay, and in static load, we'll go to element load. The load case that we have defined, right, SIDL. Now that has come up over here. We'll go to SIDL. Okay, and yeah, we also need to create the load group for SIDL, because we'll have to activate SIDL during the construction stage. So we go to this. Whenever there are three dots besides any drop down window, usually that leads to the table or the entry option. So over here it has led to the entry option for the load groups. So say I am entering SIDL, okay, SIDL group, and I'll add it over here. So in load groups, now SIDL group would be there. Okay. I'll be adding relative. If you are selecting absolute, that means you have to enter the distance. If you're selecting relative, that means 0 is the beginning of the element and 1 is the end of the element. Okay, so we'll be selecting the relative option over here. The direction is global Z. SIDL would be acting downward, so the value is minus 16.26 kilonewton. Okay, the elements are already selected, so we just have to say apply. And the load is applied to the deck. So applying UDLs and all is very simple. If it has some eccentricity, then all you have to do is you have to click on eccentricity and you have to enter its offset in whatever direction you feel comfortable with. Okay. So before I move to the temperature loads, I'll show a bit on the temperature loads. Okay, yeah, so we have already seen this. This could be created and we have to select the proper load type, because that could be used later for creating automatic load combinations based on different codes, ASTO, Euro, IRC, and so on. So based on IRC 6/2014, this is the temperature gradient values that they have provided. For positive temperature gradient, it is as the figure on the left, and for negative temperature gradients, it is as the figure on the right. So now we have to calculate, the H is given, but the width of the structure, if it is varying in this, then we have to calculate the effective width of the structure and we have to input that, and that at times becomes cumbersome. So in MIDAS Civil, the option is selected wherein for PSC type section or composite section, you can select that you have to take the width of the section from the section itself, right? So what software does it divides the section, it takes the width automatically and it applies the load. So now we'll practically do that. Okay. So if you have to select the temperature load, first of all, I'll be giving the simple element temperature. Say if the temperature is increased by 13 degrees of all the deck elements, then what will happen? So I'll go to element temperature. There is actually no need to, we'll give it temperature rise, and there is no need to create the load group, because usually temperature loads are applied in the post-construction stage. That is after everything is done and your structure is working fine. After that, it is checked for the temperature loads. So it is not necessary to add it in the construction stage, and hence no group would be defined for that. Yeah. Say the temperature is rising by 13 degrees Celsius. Apply. So the temperature rise has been applied. Similarly, from here itself, you can apply the temperature fall as well. You have to select all the elements, select the load case as temperature fall. Okay, and say it is minus 12. Apply. Okay, so now if you will view in the work table, the element temp rise has 55 loads because there are 55 deck elements. Similarly, temp fall also has 55 loads. So the temperature element uniform rise or uniform fall load has been applied. And now we'll move to the temperature gradient. Okay, so we have to select the beam section temperature. First of all, yeah, we have to select all the elements. So all the deck elements have been selected. The load case would be positive temperature gradient. Again, as I said, no need for the load group. The section type is PSC that we are using over here, right? So we have to click PSC, and as shown in figure over here, these are the nomenclatures which are provided over here. Okay, so accordingly you have to enter values. Now reference point we are taking as top. First we are entering the 17.8 and how the temperature is going down, that part. So we'll take the reference as top. We have to enter width. So if you want to manually enter the width, you have to click over here and you have to enter some value over here. Okay. But if you want to do it automatically, as I had shown in the previous slide, you just have to select this section over here. So the software will automatically take what is the width to be considered. Now, H1. The height as mentioned as per IRC is, just a second. Going by IRC, H1 is 0.15 meter. So over here that height is H1, right? 0.15 meter. But if you can view, H1 in the software means the distance of that point from the top. So the 17.8 degrees Celsius, that temperature is at the top itself. So here H1 would be 0 and H2 is 0.15. Okay, so the total distance covered is 0.15 meter, during which the temperature falls from 17.8 degrees to 17.8 to 4 degrees. So 17.8 to T2 is 4. Okay, we have to click add. So that data has come over here. Then it falls from 4 to 0. So now the H2 that is given in IRC 6, that is 0.25. So to give a distance of 0.25 over here, you will have to enter H1 as 0.15 and H2 as 0.4. So the difference is 0.25. Okay, so I'm entering 4 over here and I am entering 0 over here. Okay, I hope everyone is following. Then I say apply. Oh, sorry, my mistake. I have to add it over here. Okay, so T1 and T2 has been added. Now similarly for bottom 2.1 is there, bottom temperature, which falls to 0. But now the reference point has to be bottom. So I select bottom. Okay. I select H1 as 0. And I select H2 as, I think it is 0.15, right? I'll just verify that. Yes, 0.15. So 0.15. Okay, and the temperature from 2.1 it goes to 0. Okay, so I click add. So as noticed, 2 values are there for top and 1 is there for bottom. So once this is done, you have to select all the elements for which this load needs to be applied. Okay, and you have to click apply. So if you can view the temperature gradient load, here you can see that as your section is changing, the temperature gradient where it is applied, that also changes. Okay, if you'll go to the work group, here in positive temperature gradient, 55 load cases have been added for all the 55 elements. Right, now we'll be adding the negative temperature gradient part. Okay, for few people the video seems to be lagging, but no issues. What I've covered just now, I'll be doing the same thing for the negative temperature gradient as well. So it could be done. I'll be selecting the beam section temperature again, the load case as negative temperature gradient, default load group, PSC. First I'll enter from top. B I am taking as section itself. H1 is obviously 0, and going by IRC 6 2014, the H1, H2, H3, H4 all values I have taken over here as 0.25. Okay, so H1 is 0, H2 is 0.25. Okay, and temperature falls from 10.6 to 0.7. So minus 10.6 and T2 is minus 0.7. Okay, I'll add this again from top. Now H1 would be 0.25, H2 would be 0.5, and the temperature it goes from minus 0.7 to 0. Okay, and from the bottom we'll enter for the bottom fall. H1 it is taken as 0, H2 again 0.25, and the fall is from minus 6.6 to minus 0.8. We are adding it, and for the other part it is 0.25 to 0.5, minus 0.8 to 0. Okay, I'll add again and then apply. Sorry, so we need to select the elements and apply. Okay, so now the positive and negative temperature gradients have been assigned. So moving on with the slides. Okay, so yesterday using the FCM wizard, the entire construction stage process was done by the wizard itself. However, if you want to manually do it, then this is the general procedure. First of all, you have to define the material sections, geometry, property, everything. Then you have to assign the elements, boundaries, etc. to the groups. Then you have to define the time dependent material properties, which I'll be doing now. However, we'll be covering a bit of construction stage tomorrow since we have run out of time. So I'll just define the time dependent properties and everything. Then we have to enter the construction stage data. We have to define the tendons, perform the analysis, and then we have to check the result for each and every construction stage or as the need be. Okay, so I'll just define the time dependent material properties. Okay, so to define time dependent material properties, you have to go to properties, creep and shrinkage over here. To select creep and shrinkage. Oh, these are already there. Okay, so we are adding, say for superstructure, M50. Okay, the code is IRC, Indian IRC 112. Okay, the compressive strength for M50 is 50, 70, and notional size we are taking as 1 meter. Cement type is normal, and we'll say show results. So it will show how creep and all is changing with time. We'll say okay. Similarly, we can add for M40, so sub M40. We have to select IRC again. Compressive strength is 40 Newton per mm square. Notional size as 1 meter. And show results and okay. So creep and shrinkage properties have been defined. Similarly, for compressive strength, we have to click on the compressive strength button over here. Again, we'll be adding these. So say super M50. Okay. The code is say Indian. Yeah, by the way, you can even manually enter these values if you want to do that, but that is cumbersome and usually not done. For usual materials it could be done over here itself. Now in IRC 112 it is the mean compressive strength is given, that is represented by FCK plus delta F over here. So for M50 grade the mean compressive strength is 60, sorry, rather in this case it could be, it's in kilonewton per meter, so we'll have to change the units in Newton mm. Okay. Compressive strength, add 50, Newton per mm square. The cement type is normal cement. We have to redraw the graph. Okay. Similarly for substructure, IRC 112 for M40 FCK plus delta F is 50, normal cement. Okay. Redraw the graph and okay. I had defined the creep and shrinkage properties in different unit. So compressive strength I'll have to change over here. You can see it's 0.05, so that's not right. So we'll change it to 50,000 mm. Show results. Okay. So similarly it has to be done for substructure as well. Now once these are defined, we need to connect this, because the model or the software itself won't understand where these changes have to be applied. We have defined the materials and we have defined how it should behave, but we need to connect these. So for doing that, there is this material link option. You have to click that. For creep shrinkage, we say select sup M50. Again, similarly, for compressive strength, we select sup M50. Okay, and we select that material over here. We add it and we just have to click on this add button. When we do that, the material is linked with the time dependent property. Similarly, it has to be done for substructure. We select sub 40 for creep shrinkage, sub 40 for compressive, sub 40 for material, and add. Okay, so now the link has been made, and what would be done in construction stage and all that I would be clarifying in the session tomorrow. So as of now, this is the end of the session. Whatever questions you have, you could type in the questions tab. I'll try answering those, as many of those as I could right now. Rest will be making a document and sending it to your emails. Also, as you know, you can reach us anytime at techsupport@midasit.com. So see you again tomorrow at the same time. And also for the Mumbai users, we are going to conduct a detailed one-day workshop in Mumbai on 21st February for composite PSC eye girder analysis. So the details of those would be mailed to you shortly. You could just register and attend the event for further clarifications. Okay. Thank you.